Imagine encountering a technology that could eliminate 70% of critical and security vulnerabilities, about conservatively 50% of our energy use, and in some real-world use cases, and reduce memory use by 95%. Welcome to Rust. In this session, we're going to be focusing on three really important areas. Choosing or thinking about choosing another programming language is a really big step. So I want to spend plenty of time actually discussing some of the motivations for doing so. We also receive several questions at work about, well, what are you folks doing with Rust? And I want to answer some of those for you. But most importantly, what I really want you to get out of this session is the thought that the tools are right there for you to start building today. And it's actually much, much easier than you think. So, as I said, I really wanted to motivate Rust. And one of the things that it might seem slightly theoretical is this term called memory safety. Memory safety, it turns out, is actually a very serious problem that accounts for 70% of high and severe security vulnerabilities reported to the CVE database. CVE is sort of an international registry for where the security community kind of shares vulnerabilities in software that's highly used. The blog post that I've actually got up here provides references to multiple independent research papers actually substantiating that 70% claim. It also provides a little bit of insight into some of the ways in which AWS is attempting to really strengthen the internet by securing some of its foundations into curl and, as you'll see, into other parts of internet infrastructure. But for your business, actually running your applications faster is much more important, or at least it's much more pressing today. And there are many ways to actually evaluate performance, but I thought one of the interesting ones is actually a little bit of a focus on serverless. So Rust is a natively compiled language. It doesn't have a runtime, so containers tend to shrink down very, very small, and they tend to get deployed into serverless, say into AWS Lambda, very, very quickly. So here's a website which provides an evaluation of multiple Lambda runtimes and the time it takes for 10 cold start function invocations. As you can see, Java is still going. Rust was nearly instantaneous. If you are using the, say you'd probably go for a TypeScript or a Python, it turns out that Rust will probably finish executing your code by the time the Python interpreter has started reading your script. These are the real-world benefits that we've discovered in our services and our customers are discovering as well. You don't need to be an expert Rust programmer, in fact, and to gain some of these benefits. So here's actually a blog post I found about someone who is a seasoned Pythonista. They've been using Python for a long time for a data engineering / data science workload, and they decided just to give Rust a go. And they immediately got a 60% performance improvement. Like, they didn't know Rust. In fact, I've actually gone and had a poke in the repository and discovered that it's not really the best Rust code out there. But hey, you know what? It actually doesn't matter because they will have plenty of opportunities to learn, and the benefits to them are immediate and substantial. It turns out, by the way, in the comments that several suggestions for the code have actually been demonstrated to really shrink the blue line there about half again, which is kind of neat. But we're actually not done with the motivations for Rust. I want to talk a little bit about how this kind of boils down into cost. And here's a blog post from Tencent. And Tencent had a very large appliance that had about 700 Node.js instances running. And they thought, well, this is a really, really hungry piece of code. So they gave themselves sort of a 2-week spike to kind of do a proof of concept in Rust. It turns out their Rust implementation performed better, and they're actually able to shrink their fleet by 300 nodes. Rust will actually do better. So here's another test from one of our AWS community heroes who ran the same Lambda function 2.5 billion times and decided to evaluate whether or not, in this case, I think they were evaluating Go against Rust. And Rust did really well. In fact, it used about a quarter of the memory and still performed better than the other implementations. So we've now got multiple people with this idea that actually Rust can perform better, even if I'm not a Rust expert, in multiple different workloads. But for me, the reason why I'm at AWS, my job is actually to support internal teams use the language to build AWS's services. The reason why I'm really enthusiastic is because of the sustainability benefits that widespread adoption of Rust will have for the entire globe. Our own analysis, we believe that a conservative estimate, in fact, we're actually much more optimistic in sort of some of the internal documentation, but we believe that a conservative estimate, we could save maybe 50% of our energy use. And, but we've got all these motivations, but actually I want to give you something to be able to sort of substantiate this yourself. So it turns out that on the AWS samples GitHub repository, there are multiple implementations of this specific application. We have 4 Lambda functions that are interacting with a DynamoDB database. It's storing product information that's randomly generated. Multiple SAs, or solutions architects, as we like to call them, implemented this application in multiple different languages. And I'm about to show you the results of how they performed. I actually went and downloaded them myself and ran them myself about 10 million times. And at first I was like, whoa, maybe I should actually learn Kotlin. Because I thought that Kotlin should be, like Rust, I thought should be at the bottom here. It turns out that there's a little bit more to this story. So just in case it's not obvious, the response time is 50 milliseconds. So 50 milliseconds is quite fast. That's the time that human perception kind of operates on. And P999 is 1 in 1,000 requests. Faster than human perception. Now, but there's a strange thing that I've been talking about, which is that Rust doesn't have a garbage collector, it doesn't have a runtime, and yet a language that uses the JVM actually performs better. But it turns out that Kotlin is cheating. Or at least maybe I didn't define the problem with enough specificity. It turns out that my Rust container has a container size of 128 megs of RAM, and the Kotlin implementation is allocating 2 gigs of RAM. And it turns out the way that Lambda allocates CPU is that it will actually give functions that have more RAM more compute. So this actually provides 2 stories. One is that for most workloads, actually, Lambda's really quick. It doesn't really matter which runtime you're at. On steady state, actually, you can get very good performance out of almost every runtime you've got. The other thing, if you really want to put your function on afterburners, Just give it more memory, and then it will be allocated more CPU. Okay, but what about what I think is kind of the kicker, and that is cold start. So if anyone has used the Lambda environment before, they will have an understanding that Lambda essentially shuts off your function when it's not being used. And when it's first triggered, we say that this is a cold start. And in fact, it does a whole bunch of work getting your container set up for your request to actually be delivered a response. It turns out that all of these runtimes that have managed environments, so in the case of Go, we've got our garbage collector running that we need to kind of spin up alongside our application. The same with TypeScript, there's an interpreter as well. And Java, even the native code implementation, the Graal VM, even if you compile your code to native code, there's still a big, hulky piece of there's a big chunky piece of software that's running alongside your application that takes a lot of memory and a lot of time to start up. I've talked a lot about Rust in the abstract, and now I want to scare some people with some source code. I hope that you'll forgive me. This is a function which takes some iterable of i32. This is an integer if you're from Java, and it returns the sum of their squares. So what we do is we have a reference to some range, so some unknown length of i32s, and we return an i32. We iterate over our input, and then map, which is apply a function, in our case, an anonymous function that takes a reference to every element and then returns the square, and then sums them all up at the end. Now, you may notice if you have ever used, say, a C++, which Rust is very commonly associated with, that we don't need to manually dereference the reference. If this is nothing to you, don't worry. The thing is that Rust is actually providing what we call automatic dereferencing. What this means in many circumstances, it removes a lot of syntactic clutter, which actually sort of increases the ergonomics of the language as a developer. The other thing to note is that while this function executes, it is impossible for any other part of the program, another thread, doesn't matter, can never have read access to your input argument. No one will ever go on and delete something, or there'll never be a data race. It's guaranteed by the language at compile time to never be a problem. Rust eliminates entire classes of bugs, including iterator invalidation. But there's more. It turns out that computers have more than one CPU. But what this function currently doesn't do is provide parallelism. So how does one provide parallelism? If I wanted to sort of send all of my integers, all of my stream of input integers to every CPU core, and that's a lot of work. I've got to kind of split up a thread pool. I've got to kind of send my data around. I need to clean everything up afterwards. Or you just import the Rayon module, and then you've suddenly got a parallel iterator available to you that does all of the bookkeeping. What I want you to take away from this is that Rust is not a language that is impossible to learn. You may have heard, oh, it's really, really difficult, and the borrow checker is really challenging. The borrow checker is the thing that guarantees that nothing can clobber over your data. And maybe you will encounter problems in which Rust is more strict, but also Rust has a lot of niceties to it, like this one, that I think is actually worthwhile in and of its own right. Now, I've got two more code examples, and the next one's a little bit scary, but we're just going to breathe through it and just kind of work through it all together. We'll get there. We're going to create a web API that sends out some JSON data, And so I bring in, and we're going to put it on Lambda. So I import this Lambda HTTP thing, and then I pull some more stuff in. Axum is the web framework that we're using. Serde is the serialization library, and Serde_JSON knows how to convert Rust data types into JSON. Annoyingly, we've got a couple of different, we're overloading the term JSON in a few places, but we'll get there. This is what our index function looks like. We have a function, some function index that returns a JSON object, this type here, that our web framework understands, and Serde_JSON, one of its values. So they do actually work together, even though they're from different ecosystems, essentially. And this is the contents of that function. So let me read this out. This is sort of a constructor of a JSON object that Axum knows. And this JSON macro takes something that looks a lot like JSON syntax and essentially interprets it at compile time to do the right thing. Now we can go and we can add arguments. So in fact, the path, where's path? Path is over here. Path knows how to deconstruct a URL path into, in this case, just one component, which is a name. And we can use the name in the string itself. And the JSON macro will actually know how to go and turn this into sort of a variable substitution. So again, we get these really high-level features, and Rust doesn't actually feel like a really clunky systems programming language. At least that's my perception as someone who spent 10 years in Python. So the main function here is a little bit interesting. We've got main returns a result, which is an enum, actually, that could actually return kind of nothing or an error type. And we set up some routes, and then we run our application. That is a web API, and that is what you're able to deploy into Lambda pretty much right away. If you go and look for the examples that are in the repository, like at the last slide. So you've just got to kind of, we've got a few more minutes left, and then I'll kind of reveal. Now this one is an example of working with the AWS Rust SDK. The first two lines, we create our transcription job object, and the next four, we sort of parameterize that. This is known as the builder pattern. It's actually relatively common in Rust. Rust doesn't have what is known as bona fide constructors. And then to send it to AWS, we have the send method, and then we use await functionality. And this question mark takes the result that it returns and unpacks it and returns the OK thing. Okay, so we've got a couple of videos here, and this one is how to initiate or get a function on Lambda running. So you'll see I've got this cargo thing. Cargo is the package manager for Rust with the cargo Lambda functionality. Just sort of a sub package that we can pull in from open source. I'm creating an HTTP-based Lambda that has cargo.toml file is the metadata, and source main rs is the body of the function. It has a function handler. You can see that it's building up an HTTP 200 request. It's got some boring boilerplate in there, so I thought I'd like spice it up with hello, Sydney. And then I thought, you know what, that's kind of boring. So I thought it'd be a little bit more interesting and put in a bit of a reference for a sport that I really don't care that much about because I'm from New Zealand, but fair enough. Okay, so now we've got our source code ready. We now create up a little localhost server. On the other side, we need to invoke it. The watch thing will wait for requests. On the first request, it will compile the code. We don't take any arguments, and so I just provide an empty JSON blob. Turns out that I had a syntax error as I was recording the video, so it kind of worked badly. We turn out the CPUs kind of burn away intensely while this thing compiles. But eventually we get a result. You can see that we have kind of this ugly JSON blob, which is kind of the raw internals of Lambda. And I can use JQ to actually make it a little bit nicer. Now, if this has kind of piqued your interest, which I'm hopeful that it has, I've got one more video. And that is a demonstration of providing looking through the developer center for the Rust content. It turns out that Rust is right there, but there's a big warning sign, and I'm pointing you specifically to the examples, because I don't really read the docs. I just actually go find the examples and just try and play around with them. So I'm trying to give you some insight of the fastest way to get to the examples. There are dozens and dozens there, which are all working examples right now. And I'm actually going to dig into creating an extension for Lambda, which can be used in other functions as a layer. So that has we have another main with a result and a error, and then actually implementing this API for the extension involves invoking a call method at every invocation, and also a poll ready, which basically asks, are you ready to accept requests? Okay, the Rust SDK, the AWS SDK for Rust is actually in developer preview. That means we need your feedback today. There are big warning lights that say, do not use this in production. And I really want to add some pressure to my colleagues to get rid of that label. And that requires customer demand. AWS is very enthusiastic about customer feedback, and so please do play with it. You'll find that you will get excellent performance out of this thing. And if you are from the Rust ecosystem, the SDK makes use of really prominent libraries like Tokyo and Hyper, which means something if you're into Rust. The SDK itself, the broader SDK, is also available via the Developer Center. The broader SDK enables you to interact with all AWS services via Rust directly, and that's on the left of these four major navigation buttons. Again, I really like to show people where the actual code is and where the examples are. So, because I really think that kind of like a project-based learning approach is kind of interesting. So there's the big angry warning. This is the thing that I'm on like a personal mission to kind of change. We are actually hunting for an example application that will take some text, transcribe it, upload the transcription, turn it into speech, upload the speech to S3, transcribe the result, kind of like a full circle. Inside the examples, it's actually called the telephone application. And I'm just going to give you a very small peek as to what interacting with the API is like. The initialization is relatively common. We have this client object which interacts with the API. We create some object, we then parameterize it, and then click and then issue a send call. That's generally the way that we work. Transcription is sort of the inverse, and again, we create the job, then add some more parameters to it, and send it off. We do get quite a few questions around the use of Rust inside AWS and which services we're using it for. I want to start, though, with discussing or just touching very briefly on some of the open source projects that we contribute to. BottleRocket is a container-centric operating system. It is sort of the backbone of EKS. Firecracker is the backbone of Lambda and the backbone of Fargate. It is a virtualization system or sort of an isolation system. These are both open source projects, and there are many, many others that are available to play and sort of have a tinker with that you make use of Rust. And I'll just give a small shout out for this thing, Smithy-RS, which is actually a code generator for generating APIs and servers that I think is going to be extremely interesting in the next couple of years. And the Kani Rust verifier actually provides formal verification tooling so that you can verify in a very robust way that your API is valid. We have multiple products that have components that are built in Rust. I just want to call out S3. There's a really interesting paper you can hunt for shard store. And this actually describes the architecture of one of the storage nodes inside, like right in the bowels of S3, and how Rust was actually able to increase reliability and performance. Again, Fargate and Lambda are both serviced via the Firecracker project that we mentioned before. I said that I would tell you where to find some of these examples so that you can regenerate that graph. Here it is, GitHub/AWS-samples-build on AWS with Rust. I strongly encourage you to add issues to that. That's my repository. And I will be very active in trying to actually flesh that out. At the moment, the documentation is quite raw, but I really want to actually incubate that to make it very easy for people to evaluate whether or not Rust is an appropriate choice for them. I also wish to encourage you to join millions of people with the AWS training and certification effort to accelerate your impact. And this is via Skill Builder, which is a really neat utility that provides access to hundreds and hundreds of courses and other learning materials. Thanks very much all, and I really appreciate your time and hope that you have a fantastic journey with Rust.